I beg you tell me the place, make I know the location. Make I know the location. I get the girls from Ghana, they ready to
No,
go.
it's not so like, what is that now? What is
Them they
that
smoke
now?
anything, them they drink Hennessy. Make you plenty money, they do, I will see you. But every time I give you lamba, kilo shell gong gong, kilo shell gong gong. You know I make you book it down, kilo shell gong gong, kilo shell gong gong. Steady stacking on my paper, kilo shell gong gong, kilo shell gong gong. I make the party come alive, kilo shell gong gong. Dollar rise, no rise, come and come here. Mama feel like cool on me care. All your girls in my DM, kill one in bed. Sliding in, about the poor, get them on there. See, Charlie came, Charlie saw, Charlie conquered. Charlie going a year, you know they run down. Charlie get a tax, you know they see a tax. Charlie make money, Charlie chop like a kilo day, kill a jugono. And when you bang back, come on, you from a jugono. Oh, I'm picking the buruku, you ma come in like a anyways, me, oh my dog, come in like a hello, I see you. So your baby, I see you. Nobody back here. I see you. I beg you tell me this like you
Hi, good afternoon, guys. Is anyone online? Is anyone online? It seems to be lag. A little lag, but it'll be fine. It seems to be lag. A little lag, but it'll be fine. It seems to be lag. A little lag, but it'll be fine.
You have to earpiece, please. Come, earpiece.
It seems to be lag.
Thanks.
Come on.
Thanks.
Come on. Hello. Okay, I think we're live. Okay, so this is pretty my first ever live stream, first video tutorial, so I don't know, it might not go exactly as planned, but I think we'll all be ending doing fine. So if you're online, please just notify in the chat comments below. So this is an introduction to reverse engineering. Is the audio okay? I think I've fixed the interference already. Okay. So I think okay now all set up now. Okay, so like I said, this is an introduction to reverse engineering. Basically, reverse engineering is the process of discovering technology principles about a device, a software, a system, and then uh, switching the protocols here to going through the analysis with structure and trying to build up something based off what was existing before. Uh, so some people call it reversing, SRE. But basically, it's so basically most people have in mind when reverse engineering something to discover trade secrets, to find vulnerabilities, go for as academic research as possible as well, or circumvention. So for guys who have to build crack softwares, who have to pirate softwares, uh, they engage in reverse engineering as well. Also complaining about the audio sound interference. Is it fixed now? I guess it's fixed now. Can you all hear me? Hello? Hello? Can you all hear me? I don't know, the audio is terrible. Okay. Talking about reverse engineering. Basically, reverse engineering is the process of discovering technology principles about a device, a software, a system. Going through the analysis with structure and trying to build up something based off what was existing before. So some people, but basically it's so basically most people have in mind when reverse engineering something to discover trade secrets, to forget. Also complaining about the audio sound interference. Is it fixed now? I guess it's fixed now. Hear me? Hello? Can you all hear me? I don't know, the audio is okay. I think terrible. I've fixed the audio now. Okay. Okay. What's the device, the software, system. Going through the analysis with structure. Basically, most people have to forget. Also, hello. Can you hear me?
Okay, so
I'm just gonna open up audios. I think I've
disassemble
file
file
now.
software.
Going through the analysis structure. Basically, most people have to forget.
Disassemble. Don't know why this is. Let's try the machine. Disassemble. Okay. Don't know why this is. Let's try the machine.
Okay, for some people, audio is fixed already. For some people, audio is still broken, but I think it's the internet here. Okay.
Okay. Don't know why this is.
So like I was saying, so the reason why most people do reverse engineering is because they're looking at discovering trade secrets. So a rival organization is trying to build off someone else's product, and they have to reverse engineer their products, be it hardware or software, so they can discover trade secrets. It could be to find vulnerabilities. So for bug bounty hunters,
So like I was saying.
security researchers trying to find vulnerabilities in the hardware or software. Uh, also, it could be they can discover trade secret find. Also, it could be for purpose of academic research or purpose of making pirated copy of that software. That's for circumvention. So that's reasons why most people. Also, it could be just to analyze protocols. So it could be regards engineering a network device, just to analyze the protocols. Understand? So I think a couple of days ago, I was doing someone's research about reverse engineering Skype just to understand network protocols, and he found a way to create a backdoor in Skype off that. Yeah, it could be out of pure curiosity. So the fact that you're just curious about looking through the internals of a binary or piecing apart a hardware device, yeah, and maybe just to patch the binary and alter the behavior of the software or the system. Yeah, sounds cool, awesome. Okay, I think there's this slide I'm using here, checkpoints. Just going to go through with this. Okay, come here, please. Over here. Okay. Full screen. I guess you all can see this. So, like I said, this introduction to reverse engineering. I've talked about what reverse engineering is already. It's basically going through stuff and trying to understand the internals, understand how it works, it's processing, and trying to build up something based on that. Uh, yeah. Then, so why do it? Like I said, discover trade secrets, find vulnerabilities, academic research, all and all. That's just story part of it. Yeah. This looks awesome, cool for the culture. Yeah. Find the vulnerabilities. Uh, yeah. So now this is the catch. It's pretty much what discourages a lot of people from doing reverse engineering is that it's pretty much low level stuff going on here. Pretty low level stuff. I was trying to open up a binary just now. Okay, I think ID is up. My virtual machine is up. How to this here? Um, can't see. Hopper. Yeah, so I just want to open up a binary and explain little stuff there about the low-level assembly. Okay, so first thing is that computers interpret software or just can only understand machine language, and the closest to machine language which we humans can understand is assembly language. Uh, so it's a trade-off in having to build your software in high-level language, programming language, and then in trying to understand the internals, you have to be able to reach low level language, which assembly is the lowest of, just next to machine language. Uh, okay, so it's a skill that is required of us engineers to be able to intimately understand um, these binaries, to go through these analyze binaries basically. Uh, so to be able to do to read assembly language. Um, I'm trying to look for it. Okay. So let's say for example, I pick this up. Okay. So I'm trying to load up a binary in Hopper. Now Hopper is a disassembler I use. One of my favorite disassemblers for analyzing binary. So basically, disassembler is one of the tools you come across when doing reverse engineering that you could use to break down the binary. You see the internals of the binary. It translates the binary basically to assembly language. You could something readable for humans. Be able to identify strings, basically functions, processes, and then you could analyze the binary registers as well. Okay, so basically this is in simplest form assembly language. This is start of a procedure, and you see random mumbo jumbo like this. Like for example, so EBP, pop, ESI, move, ECX, ESP. This is unintelligible stuff, right? It looks unintelligible, but this is assembly language. And so for you to be able to do binary analysis or reverse engineering, you should have pretty understanding of this um, stuff here. Uh, so that brings me to a little introduction on assembly language. Okay, so in assembly language, we have instructions, we have opcodes. So these are basic instructions in assembly language. Most of the commonly used instructions in assembly language. Move, MOV, that's move. pop, so pushing something off a stack. Okay, so this, like I said, this video is just an introductory video. I won't go too deep into assembly language now. Maybe in a later video, I would do much of assembly language. But I just wanted to get familiar with reverse engineering, the whole concept of reverse engineering, playing around with the tools used in reverse engineering. Okay, and okay, so I'm going to just run through this. Back to our slides. Slides, where are you? Okay, yeah. So like I said, this is pretty low level stuff. Yeah, and I mentioned that we have opcodes, we have instructions in assembly language. So an average opcode size is 3 bytes. Yeah, and so looking for assembly language is basically like looking for a needle in a haystack. It requires a lot of patience, a lot of basically a lot of patience in having to find out what exactly you're looking for. Uh, yeah, and sometimes when you're trying to reverse engineer a binary or a software, you find out that most of the times even for people who have pretty good understanding of assembly language, they find it uh, unintelligible stuff. Like it's pretty illegible. You can't understand what you see because software developers now find a way to obfuscate their code, and then they use a packer to try and reduce the size of the software they're pushing out. So those packers make it uh, just basically obfuscate the code, and you can't understand the disassembly if, you get. Okay. Uh, so running just ignore all this stuff. Okay, yeah. So basically, this is a flow process in reverse engineering. So an auto writes a code, a reverser reverses it, auto creates an anti-reversing technique, and reverser bypasses it, so on and so forth. It's a back and forth game between the software developer or the code author and the reverse engineer, both going back and forth. Okay, yeah. So resources and tools we use for reverse engineering. Basically, use a debugger. If you're going to be doing dynamic code analysis, your best bet is to use a debugger. So dynamic code analysis is you're analyzing the code on the go. So while the application is running, I'm talking in terms of software reverse engineering now. So while your software is running, you're analyzing the code. So for every call the application makes to system functions, you tracing them using a debugger. Uh, Favorite debugger of choice for me is the GNU debugger GDB. You okay? So GDB. Yeah. GDB comes by default on Linux-based machines, but for Mac systems, I guess you have to just install it. Just brew install GDB. Yeah. So this is GDB. Like I said, I think my screen is pretty small. Okay, I'll increase this. Okay. Yeah. I think this is better now. Okay, so GTB is open up. Yeah. So I'm just going to try and run a file. So GDB slash bin slash sh. Yeah. So this is my default shell. I'm just trying to debug my default shell here. Okay. So when I do this, we could now analyze the file as it's running. Let's say run. Seems to have failure. I think I know the reason why. My GDB is not code signed. Well, we can as well have this done in Hopper. Okay. Okay. So the desktop. Okay. So GDP. Okay, so GDP.sh. Okay, here we go. Yeah. Okay, so I'm going to run this. So starting program. So you see, it's starting program. It's running the bin/sh. So it open up the shell, and you can now executing any program. So basically, like I said, uh, every single call that the application makes inside the debugger, you can trace them. You can see what is being made. So you see when it's started executing a new process. This is, oh no. Apologies. Okay. Yeah. So see, when we tried opening a new process is executing new program, look at LS. Then uh, trading, showing the trading performed. This is the call to the the, the library being used. Live trade, live trade, db.so. Okay, that's a Unix library system library, and then it now lists out the file. So performs the operation. So this is the operation listed, which what I was trying to run before, listing files available. Yeah. So we can analyze a binary simple like using a debugger like this GDB. Another thing, also we can do static disassembly. Okay, let's go to the same again. So static disassembly, for example, we can run. So GDB has help. You could run help inside GDB to see most of the commands. So it's just pretty simple. Like I said, if you have basic command flow, basic around the command line, you can find your way around. Okay. So basic, let's say I do this main a simple ditch. Okay. Okay. Yeah. Okay. So I just run a command for disassembling the binary, the main function of this particular binary. As you can see, we have our assembly language, mumbo jumbo stuff here. But it's something over time you will get to understand. And once you see disassembly like this, you can interpret it and tell what the binary does. I'm going trying to go to the top. Okay, so basically this is static, a little bit of static analysis. You disassemble the function. Yeah, a function. Now, first thing is every binary has a main function or an entry function. So those are the first places to look under the hood when you're trying to disassemble the binary. Look at the main function, and then from the main function you can see what calls to other functions, and then you can start disassembling. But this is basically a static analysis where you can look at the code structure in assembly format and then make analysis. Uh, so I'll go back to our slide. Okay, so I said it's a debugger for dynamic code analysis. So for debugger as well, I also have other tools I use. So I use as well. You can use Hopper, which I was trying to show here. So this is Hopper. Hopper, please. Okay, so this is Hopper. You can do both static and dynamic analysis using a tool like Hopper. Basically, load up your binary. It gives you a, a binary assembly out view. Uh, Here you can see procedures. Remember, I said we have always have a main function, and then have an entry as well. Okay, there's no entry in this place. Okay, but then there's a main function, and then so this is the main function here. Now this is the same binary I opened in GDB just now. So if you notice a similarity between the assembly code here, the one in a Hopper and the one I opened up in GDB. Also, you can identify strings. So this is simple with identify strings here. So for example, these are error messages or comments. So comments are strings. You can identify comments. It's a guide. It provides a guide for you when as analyzing a binary. From the comments that were hard coded into the binary, you can have an overview of what the file binary does. Okay. So we know from this one that this binary attribute sorry if the expected procedure is not followed. Uh, okay, this is a lot of strings in here, a lot of things, random things we really don't need now. Yeah, as well you can see. Okay, this is still random stuff we don't need. You can also as well have what's in here? Yeah, a hex view. So you can have a hex view of your binary, uh, where you can look at the headers, the hex headers of the binary. Yeah. It's just like consolidating a lot of tools into one, which is what Hopper does. There's also Binary Ninja. Um, okay. Binary Ninja, basically same thing as Hopper. But for me, I like having to try multiple tools because it gives me, I can analyze the binary from different angles. Okay, so I'm just going to try and open, yeah, I think I've opened it up before. Yeah, this is it. So see, Binary Ninja, sorry, Binary Ninja has a very nice outputting view. Yeah. So it segments each function. So this is our start function. Okay. So instead of entry, they use that start was used here. Maybe there's a function called maybe here. Another function called sorry, and then the main. Okay. Trying to load up the main. Yeah. So this is the main. So see, it's exactly the same thing we had opening up Hopper and GDB. You can as well decide to switch. No. Okay. So you can switch to a string view and look through the strings of the binary. Now, so this is basically your string function. Sorry, string, basically string in Linux where you have a file, so which is and you can just call strings, then the name of the file. This is basically the first thing I do when I have a binary to disassemble. I try and see if I can locate any known strings. So the string, the string command basically picks out a printable ASCII characters and represents them on screen in a readable format. So this, okay, I saw something attempting to, okay. So basically, this is the this is strings that were embedded in this binary, and that this string command found out, which is basically the same thing we have here. The same strings we have here. So if you scroll down to the bottom, you see basically the same strings we have here. So, like I said, these tools, disassemblers, or right, okay. So disassemblers, debuggers, they're just tools that consolidate other command line tools which we use on Linux or Mac or even on Windows. So it's just trying to simplify the process. So instead of you having to manually enter some of these commands, the disassembler or the debugger just does those operations and you can now check through. You can as well check linear disassembly. I'm trying to load. Okay, yeah. So this is a linear disassembly of our binary from the main function. This is a linear disassembly of the sorry function as well. And then maybe, so at least we have an overview of this binary now from this, that there's a main function that performs the calls to other functions, sorry and maybe. Uh, so there's also a, okay, yeah. So basically this. Now, if we have a binary to analyze, so let's say at work you get a malware, you have to do malware analysis on the malware sample, and the malware sample is a binary file. So basically, what you can do first thing I recommend is you have your file now. Simple run the file command on it, file command against the file. So in this case, our file is 100. So once you run this, it tells you, oh, okay, so this is an
ELF 32-bit LSB executable file of architecture Intel 8030, 8386, 8, okay, uh, for Linux and GNU systems, statically linked. I would explain statical linking and dynamic linking later on, uh, not stripped. Okay, I think I just explained that now. So uh, we have statically linked files and dynamically linked files. Uh, basically, okay. So in I think most of us have an overview of software architecture already. But then when having to build your software, uh, so there are trade-offs. Like for example, having to build, okay, statically linked file. I think this is simpler. Statically linked files are files that or functions that you statically define in your software, in building your software. So you have a okay. Uh, So you're they are basically like modules, yes. That so you have static modules that are defined inside the software, and dynamically linked files or libraries, as the case may be, uh, libraries that you call. So they are basically like system libraries. You call. I think on Windows we have them as DLLs, dynamically linked libraries. On Linux is they are .so files. Uh, you have them for dynamically linked files. They are files that are resident on the system, the operating system, and then you just include them, call them in your application. So, for example, if you're writing a C code, when you see something like, let me see, you see something like include, okay, I can't find anything else. But you see an include header.h, include stdio.h. Those are dynamically linked files. So they are or dynamically linked libraries that are resident on your operating system, which you just call in. So, like I said, is a trade-off between having to write your own statically linked functions and create a bulky application, or write using dynamically linked libraries and write something that is very portable, lightweight, but there's a possibility that the operating system is going to run on doesn't have those libraries. So it's just a trade-off between having to use statically linked libraries or dynamically linked libraries. Okay. So like I said, we've run file command against this binary. We've seen this as the outputs. Uh, so next thing is to check strings to see if you have any identifiable strings. Strings. Yeah. You could as well do. So if you're looking for something specific, let's say for example in this case you're looking for something like say success, you could just grep through. There's nothing success. Now it's case sensitive as well. Okay, so great. We have an occurrence of the word success here, the string success here in this binary. So with this command string, you can have a pointer to what goes on in this binary. Uh, yeah, so you can basically identify strings. That's that. Uh, you can do all this inside Hopper or Binary Ninja or IGA Pro, which most people prefer to use. So for me personally, I prefer using Radar R2. So this is Radar. I think it's an open source disassembler, debugger to command line based. Then you have, as well have the GUI. You have a GUI, a web based GUI for it as well, with cool material design. But so we can now you have this. You found out strings you want to identify on this binary. Uh, Next step I do is to run ltrace. Remember I said you can trace, uh, run a trace on the binary. You can run a trace on the binary to. So this is part of your dynamic What's it called again? Dynamic code analysis of this binary. So L trace / 100. So you see, couldn't find. Now this particular this thing, since it's statically linked, there's something missing. So a particular library missing, which is trying to call, or which possibly my Linux machine doesn't have. Yeah, and then sorry, the output. Okay. So at least L-trace gives you a pointer to what the binary, what calls are made. You can as well use strace. That's another command. These commands come by default to the Linux operating system. Yeah. Okay. So you see, with strace, it shows the process that was spawned, the process ID. Runs in 32-bit mode. Uname. So this is what is trying to run. The username. The user is trying to run as. There's a break called. So basically, you have an overview of the system calls. Okay, here you can see a write call, write sorry. So uh, it writes sorry to screen. Now you can tell if something, if it doesn't find, which in this case if it doesn't can't access this, it writes sorry to screen. Mm, okay, so that's that for dynamic analysis. Personally, I prefer to do static analysis on static code analysis on binaries using a radar. You can also do dynamic analysis using radar as well. So open up the binary dot slash. Okay, cannot initialize dynamic strings. Okay, so you run analysis on. Now you could do a single A. A is okay. So radar is a self-documenting as I say, which you can, so you can just issue a question marker and it brings a help menu for you. This is a help menu and it's pretty straightforward. Yes. Okay. So here we have analysis commands A. So if you run A question mark, it shows you all the possible analysis commands. So you can say analyze bytes, analyze all, which is AA, which is what I'm going to do next, or AF to analyze functions. Okay, so let's say AA. Now you see again, you also have help for analyzing all. You can try to do AAA, auto-name functions after analysis, AAC, analyze function calls, AAD. So as many as possible. So personally, I prefer to do AAA, and it analyzes the binary, does a straight run on the binary. Okay. Uh, so you see, it does analyze all flags, starting with a SYM dots, an entry, analyze the length bytes of instructions, analyze function calls. Then it's trying to emulate code to find computed references. So analysis is still running. Now this is taking a while. It's not supposed to take this long. I have my idea why. I think we're having a couple of errors here. Please, if you have any questions, please ask. I don't know, we're having lots of errors here. I'm just going to go ahead and stop this. Okay, so I'm going to try another binary now. I'm going to try and analyze another binary. Okay, I'm going to open my terminal here. Okay, great. So I'm going to try another binary. I think the first one was having an issue. Now this particular binary is one of the CTF challenge from I think ABCTF 2016. Yes. Yes. Okay. So if we run the binary, which is this particular one, this is the binary, right? Oh, so first thing, like I said, first thing is to just run the file command on it. So it tells us this file is a Mac O 64-bit x82 64 executable, right? So Mac O is a Mac O 64-bit executables for Mac operating systems, and we're inside Kali right now, so we can't run this file in here directly. So what to do? I'm just going to use radar to analyze this binary. So okay, like I said, you could do AA inside radar once it's running already. You can as well do it set radar to so you could use it as an argument analysis. So that's A. Okay, I think I should just do the help here. That's help. Yeah. Now this is quite a lot. Okay, so this is it. So this dash A flag runs the AAA command to analyze all reference code. There are other flags as well. So slash dash D debugs the executable file or the running process ID. So I'm going to just do that. R2 dash A. Sometimes I personally like to add multiple commands, multiple A's to it. What else? Okay. Dash D for debug, then the name of the file. Okay. So this is it. So you see, it starts debugging the process. assuming file paths. Okay, analyzing all flags starting with sim.entry. So it's done the analysis to function calls already for us. Okay. So now Radar has a lot of interesting commands. Uh, for example, we need to look at the disassembly of this binary now. All you need to do is use the command print disassembly function pdf. Okay, before we show disassembly function, uh, first thing I do is analyze functions using AFL. So AFL shows me the functions that are function calls that are made, the major function calls that are made, not to libraries now, but as written inside the binary. So we have our entry as written inside the original software. So we have entry, we have totally not the flag, and we have execute header. Okay, so let's look at entry. Now you can jump to the entry function directly by just using the seek command, which is s and entry. So if you do this directly, you're directly into the seek function, and now you can run pdf, which is print disassembly function in this for this function. So see, we have a pretty colorful disassembly here. Okay, so this is our entry function. Now, all these, like I said, these are opcodes. Sorry, these are instructions. These are opcodes, and these are address positions. So address references for each instruction on the stack. Okay. So if we go down now, okay, something a quick one about instructions. We have basically two instruction sets, assembly language instruction sets. We have the AT&T instruction sets, and we have the Intel 32 instruction sets. So IA32. So the Intel instruction set is called IA32, and the AT&T is just AT&T instruction set. So personally, I prefer to use the Intel 32 instruction architecture, which is what Radar uses, which is just basically this. So for this instruction set, what you see is add AL bytes ROX, where ROX is your register, bytes is being, so in this case we are adding a byte to AL and it's stored in the ROX register. So let's look at another instruction. So I think because it's not a regular Linux executable, ELF executable, so the instruction sets are looking a bit the instructions are looking a bit different. But here you can see a string plainly written. Where could the key be? So this tells us this binary looks for a key. Basically, it tells us that basically this binary looks for a key, tries to uh, tries to locate a key. Okay, so making headway. Um, yeah, so this is another instruction set, another instruction JE. JE is just instruction for jump to this address. It makes a jump to this address. Uh, there's there are others as well. Emulate. Okay, so let's ignore that for now. Yeah, there's a stack guard here. Just gonna ignore that for now. Okay. So we've seen our disassembly function, printed disassembly function. You can also have a visual overview of this disassembly function. So you can either use the v command and gives you, so it takes you to hex. This is the hex view. I prefer using VV, yes. So it gives you a graphical display. Okay. Okay. So you can just navigate using your navigation bar. Something I forgot to say. So Radar comes pre-installed, comes directly pre-installed with Kali if you're using Kali. If not, you can as well get it from GitHub. You just clone it and follow the instructions in the README and install. Okay, so this is it. Units like reverse engineering framework. So it's my favorite framework for reverse engineering. Yeah, okay. So you could follow the instructions here to install Radar. Uh, Basically this. So you just clone this repo, this Git repo. If you're using a Mac device, Mac system or using Windows, yeah, Radar works on Windows as well. Okay. So this is it. Like I said, so we have a visual view of disassembly. So now you can trace. You can as well here trace the logic of this binary. So there's false and true. So if an operation is carried out, so for this one now, if a jump occurs here, we if the jump occurs here, we take a true part. So this means after this jump occurs, next thing will be to move. Next thing is to move up to it's a follow a jump. Take a jump to this address. It takes a jump to this address and follows this arrow down here. So you could as well follow the jumps. Follow the calls here. There are functions for that. I think that should be true. So you use T or F here. Okay. So you can select a block as well here. Which is that now? I can't remember the command, but you can select a block and then follow the true or false calls. So at least this gives you an overview of the binary, and you can now run through. Okay. Like I said, Radar has a R2 has a visual mode as well. So that should be Ctrl Shift T. Okay. So R2. Yeah. So that should be C equals to H. Yes. So this opens a web interface for Radar. So if you're not pretty cool with a command line interface, you could as well use the web interface. Okay, then the name of the file. Yeah. So in this case, okay. So see, it starts up a server and connects. So just simply need to open this up in browser. Open link. Okay. Wow, what happened? I have no idea why. Same file not found. Okay, I think it's. Wow, this is serious. This is pretty serious. I have no idea why this isn't. So let me try it here on my Mac. Wait. C equals H. That's much. Okay, so the name of file was haha. Okay, yes. Okay. I have no idea why it is happening. A lot of things are broken here. Okay, that should fix. We'll put it fix. But I sincerely don't know why it's not opening up. It's also have a GUI interface. Can't say why. Okay, so let's continue with our binary. Like I said, you can do AFL to analyze the functions. Now you can as well, now since we have something that looks legible here as a function, we can move down there and say seek sy dot totally underscore totally. Okay. We can do a PDF here, print as a function, or a VV to show disassembly. So with this, at least you can have an overview of how the binary is like, or what each function call is like, the jumps that are made from each function calls, how the instruction sets, uh, how the instructions are being followed. Okay. What else? Okay. Yeah. So another thing is Radar has a. I'll try to solve this particular challenge though. Uh, Radar has this function called. I'm trying to remember the name now. ESIL, yes. ESIL. Okay. Yeah, ESIL. So ESIL stands for. Uh, So basically, you can emulate this thing emulates the binary running on another architecture. So in this case, where this binary is for Mac architecture, Mac O architecture, and uh, we want to emulate it on a Linux machine. So okay, ESI stands for evaluatable strings intermediate language. Uh, so you can use it to basically emulate the binary. So in this case, we're going to be so first thing is to start up your ESIL. Okay, before we go there, so we know since binary, we know our binary is Mach-O type, and we have come to the conclusion that since we can't directly run the do that dynamic analysis of binary inside your database, we have to use ESIL. So either you try to reverse. Okay, first thing, sorry, let's backtrack a bit. When we checked, okay, when we check this entry, check the disassembly of this entry, and we see a string here. Where could the key be? Like I said, it's looking for a key, and the length is 25 characters. So we could try to manually brute force it and get the key, which is 24 or we could just now there's a jump here made, and this jump, no matter what happens, it will always be false because see, if you see the way this this branch is the false, it always calls a false instruction. It always follows the false instruction. So best thing you can do is use this binary, run it, and using ESIL. So okay, let me go back. First thing is if so we see the functions here, and we make a v at entry. That should be v at entry. Okay. Now, like I said, there's call here, And then if you go down a bit, you will see a call to that totally not the flag. Where are you? That's what I'm looking for exactly. But if we jump, do a short disassembly at totally. Yeah. Okay. So we see that no matter what happens, these calls are never made. So it's either we try to, like I said, try to brute force and get what the flag is, what the key is, or use ESIL. So in this case, we're using ESIL to disassemble. So start the ESIL engine using a AEI. You could check it out later though. AE question mark. So AEI is to initialize the ESI virtual machine state. AEIM to initialize the stack. Then AIP to initialize the program counter. So we've done AEI, AEI, AEIM, initialize the stack, and then AEIM, IP, sorry, to initialize the program counter. Like I said, I'll try and give a little explanation of assembly instructions later on. Okay. So we have this now. I'm going to try and open it again here. Okay. Okay. So if we look here, yeah, okay, this looks pretty simple now. Yes. I think because I was disassembling, so I made a mistake earlier on. Because I was trying to disassemble. Wait. Uh, because I was trying to disassemble, I ran the disassembly this thing argument in the flag, so it was obstructing our analysis of the binary. So this time I removed the D and tried to run it without the D option. Okay. So AFL, yeah. Okay, I think here. Okay, great. So there's a call to a decrypt function. I think this is better now. Call to turn on the flag function, entry function, stack check field function, printf, string length function. So we know that the basically this binary checks for length of the string, and then outputs prints out something to the screen, and then there's a total flag function, and there's a decrypt function, which means that we have something encrypted basically. So like I said, we are using the okay. So since you can see this now, so we are entry no. So that should be view, sorry, at entry. Okay, great. Yeah. So here I can. Okay, yes. So now I think this is the proper graph view of this assembly. So you see, first thing is called the main being initialized. Variables are set somewhere here. There's a push to ROBP, the base pointer, and then the stack pointer is copied into the base pointer, and value. Okay, this is 16. So the hex value of a OX10 in decimal is 16. Is copied to the stack pointer. Okay, so a lot of instructions going around here. Substitution, where the 4 is substituted into EX. EX. I think I'm missing out something. Okay. But basically, there's a jump here to this address. Okay, I think this is better now. This is a better view. I used P to switch the view so I can get the addresses. So there's a jump to this address, this particular address, F1A, 0F1A. And if we look 0F1A, if we go down, okay, it's somewhere here. So if the you successfully substitute this, if the binary successfully substitutes value 4 into EAX, this register, we should get a jump to this place. But if we can't get this properly substituted, or this comparison doesn't pull through, this comparison of EAX equal to 0, then it calls this other function starting on the flag, which is what will always happen because directly before this comparison, there is a substitution 4 into EAX, and we need to have EAX to be equal to 0. So we're going to use the ASIL to do that. Okay, so first thing is to set a breakpoint. Since we know this is where the comparison happens, set a breakpoint here at this address. I'm going to copy it here. So you can, okay, from this help, you can set a breakpoint using AASU. So step onto a given address. So AESU, the address we just copied. So set a breakpoint here. So it performs a step until it gets to this given address. I don't know why it's not running now. It's supposed to have shown us breakpoint sets. Okay, but basically I think this is too much. I'm even pushing at one go. But I'm just trying to show how a binary can be analyzed using radar. Yeah. So I've talked about debuggers. Back to the slides. Oh, okay. So these are a lot of other tools that I use for reverse engineering that I didn't mention. Only debugger. Only debugger is a Windows debugger, one of the oldest debuggers. Comes on Windows, and Only debugger has been around for a long while, pretty long while. There's a port on Linux now for Only debugger, so you can run Only debugger on Linux using Wine or Mac. Um, then we have disassembler that I mentioned. There are debuggers, there are disassemblers. So it basically a debugger is it's for the dynamic. Disassembler is for static analysis. Okay. I don't think I ever used this disassembler, but for like I said, Binary Ninja and Hopper and IDA Pro and Radar. So the four of them, they work as disassemblers and debuggers all in one. And then we have a GDB, which are GNU debugger as well. Skipping all these. All these are pretty old tools. They're still applicable nowadays, but they are pretty old tools, and we have tools that does. We have tools that performs the functions these older tools do as well. So we have a IDA Pro, which is, like I said, the holy grail of disassembly. It has support for plugins, so you create your own plugins in it, or do scripting in Python. It's multi-architecture, so you can disassemble across different architectures. Has cross-platform support, so you could be disassembling Mac O or ELFs, that's binary Linux executables, or PE, which is a Windows portable executable, Windows architecture files. Yeah. Yeah, so one thing that's prominent to note is a hex editor. Uh, okay, so like I said, each of these assemblers, the buggers, they have a hex editor inbuilt with them. Uh, so you don't need to have a standalone hex editor. Uh, P Analyzer is a very popular Windows tool for analyzing a Windows executable specifically. So you just run PA Analyzer is against. Okay, so I don't have a Windows machine here right now. If not, I've shown you how to use PA Analyzer. So basically, most of all these tools are Windows tools. Yeah. Okay. Yeah. So this is something I should have done before jumping directly into disassembling the binary. We have registers. Uh, we have general purpose registers. Basically, registers in all. General purpose registers, index registers, segment registers, and the flags. So a general purpose registers could be 32-bit registers, 16-bit or 8-bit registers. So these are the EAX register, which is I'm coming on general. Uh, General purpose registers. This is an image. Okay. So, yeah. So we have general purpose registers. The AX register is the accumulator register. Uh, we have the BX, which is the base register, CX count register, and DX data register. We also have so eight. Okay, I think I should backtrack. For general purpose registers, we have eight registers in all. Um, Starting from the bottom, the base stack pointer. Uh, so that's sometimes a EBP extended base stack pointer. Then SP is our stack pointer, which you commonly see as E. Trying to look for them. Okay, this is accumulator register. EX extended accumulator register. Uh, these are base pointer. Uh, Base pointer here. These are stack pointer here. So we have base pointer, stack pointer, destination. Um, there's destination index, there's source index, there's data registers, and then we have count registers, CX, base registers, and accumulator registers. So these are basically the general purpose registers, eight in all. They are split. Okay, so you have the top four split into two, but 8 bit, 8 bits. They're all 16-bit registers. Mm, so basically, these registers they are like stores, as the name implies, registers. You store values into them. Okay. Uh, a lot of other registers, but I think for now we should just make do with general purpose registers. Static reversing, okay. So we've done a bit of static reversing already, trying to analyze the binary using its assembler. In this case, we use binary ninja and hopper to just look through a binary. That is static reversing. Uh, then we also looked at dynamic reversing. we looked at static reversing first, like I said. So we have binary ninja, hopper, which are popular disassemblers and debuggers you could use to do your static reversing and also dynamic reversing. Uh, then we looked at GDP, and we also looked at radar as tools for disassembly. What else? What else? What have we not talked about? So I think that's basically it for an introduction to reverse engineering. So I'll put up in the comment section below. I'll put up resources, more resources on introduction to reverse engineering. I think that's all. Like I said, this is my first attempt at teaching reverse engineering, so I know it was a bit clumsy. Things are not really organized, but it's a start. So frequently I will try to do other tutorials that will be more detailed and focused on a particular subject, a particular point, subject in reverse engineering. This is 6:21. We've done approximately 1 hour 20 minutes. Thank you all for your time. If you have any questions, please put the questions in the comment section below. Thank you all for your time. You do have a nice day.